All right, so for 10.1, which is what we're looking at today, we're looking at the first part of it. So we're going to look at this term homologous series and kind of what does that mean and what does a homologous series look like. We're going to talk about the different ways we can write formulas. So we'll talk about structural formulas, and we'll also talk about like what does the full structural formula look like versus the condensed. And then we're also going to talk about what's called a skeletal formula and empirical and molecular formulas. And then the last thing that we're going to talk about today is we're going to start looking at what are called functional groups, because functional groups are where parts of the molecule, you'll have different elements bonded rather than just hydrogen or carbon, which is usually what we have most of the time in organic compounds. And so what we'll have to do is you'll have to look at a structure, and based on what elements are in it, you will have to look at or identify like what functional group it has and what class it would be. So that's kind of these bullets right here, is identification of all these different classes, and there's all these different words that we're going to go through and look at them today. And the class depends on the type of functional group. So this next bullet as well, all of these different functional groups, that's really what we're mainly going to look at today. We're not going to get into doing any names or anything. We're going to save that for next week because there's a lot of information to go over. And then, as I said, we're going to kind of look at the differences between some of these formulas and how do we tell them apart today. Okay. So kind of going down here on the little statements, we're going to look at this first one and the second one. And we'll kind of start doing the third one because we're going to look at the different formulas. You're not really going to totally be able to identify them yet, though, because we're not going to get into the naming rules until next week. So we should maybe be able to identify a functional group from looking at the structural formula of a molecule, but we're not going to be able to like fully know like the name and all the information. All right, so first part on here deals with this term homologous series. So in science, the prefix homo is used a lot. We see like in biology, you have homozygous and heterozygous. In chemistry, we have homogeneous and heterogeneous mixtures. So it's kind of the same principle here. That prefix means the same. So if you have a homologous series, what it is it's a series of organic compounds of the same family. Okay. And so by family, we mean that they have the same type of functional group and they only differ by one CH2. So their formulas are almost the same. So if we look at these three examples they've given us, if I look at this one over here, if I wanted to kind of condense its formula, it would be CH3OH. Okay. What's drawn here, this is the full structural formula where I'm showing all of the individual bonds to the hydrogens and everything. But I can condense it and I can write it like this, and I do CH3OH. Now, if I do the same thing to the one in the middle, then I have, so here there's a C, so I can see there's a CH3. After the CH3, the next little part of the chain is a CH2, and then there's that OH on the end. Okay. And then the third one, all the way over here on the right, I have CH3, which is kind of starts out here. And then there's two CH2s, if I see them here. So I'm going to do CH2, CH2. I have to write it twice, and then the OH on the end. So if you look at these molecules, the only difference is I'm adding CH2s. So here I had CH3OH. Here I've added a CH2 group. And then the next one, I added another CH2 group. And so these would be considered a homologous series because they have the same basic pattern in their names. They all have like that OH on the end. The difference is I'm adding a CH2 group, and that makes them different formulas, but they're in a homologous series. Okay. So for this one, if I want to kind of give some information on them, the functional group that they have is that OH, and we're going to look more at the functional group stuff later in more detail. But for right now, we would just kind of identify this is a homologous series. And if I wanted to sort of classify it, I would say, well, their functional group is the hydroxyl group. That's what I call anytime I have that OH on a molecule. And each member differs by a CH2 group, so that's how I know that they're a homologous series, okay? If you have a homologous series, the compounds that are in or molecules that are part of a homologous series, they have similar chemical properties because it's like they're a family, right? So they're going to be slightly, react the same and have similar properties. They show a gradation in physical properties. So for example, physical properties would be like boiling point, melting point, density, that kind of stuff, solubility. And so what the biggest example they give here is you have increasing boiling point of alkanes. These three right here, all of these are in the alkane family because they all have just carbons and hydrogens that are all single bonded, okay? And so what happens is this first one, this is CH4. The one here in the middle, this is C2H6. And then the one over here on this side is C3H8. And so they're a homologous series, they're a family. They're going to have similar chemical properties, so they're going to react really similarly because they're in the same family. But their physical properties are going to show what we call a gradation, excuse me, I'm saying that wrong. So for example, the boiling point is going to increase as the molecule gets larger. So CH4 is going to have the lower boiling point, and then C2H6 will be a little higher. C3H8 will be even a little bit higher than that. And the reason is, as we're going to talk about later, and when we get into more into properties next week and the week after, the larger the molecule, the more molar mass it has, and so the more energy it's going to take to kind of break apart some of its bonds and turn, or not break its bonds, but to break the molecules apart to turn them from a liquid to a gas. Okay. In general, for alkanes, they have this basic pattern they follow. The number of carbons, when you're given that, if you want to find out the number of hydrogens, it's always going to be double and then plus 2. So let's say I have C4 and I want to know, well, how many H's would be in the formula for it to be an alkane? Well, I would double that 4. 2 times 4 would be 8, and I would add 2, and so it would have to be 10. So if it follows that pattern of the number of hydrogens is 2 times the carbon plus 2, then you can safely identify that compound as an alkane, okay? So to kind of wrap up for the homologous series thing, they differ by a CH2 group. The general formula is the same, but they're going to be either longer or shorter chains because you're going to have more or less CH2s. They have similar chemical properties, but they show a gradual increase, a gradation in physical properties of such as boiling point, and that's due to the larger molecules having a larger molar mass. Okay, so second part here has to do with these different ways that we can represent the formulas. Okay, so there's 3 examples on here. When you watch the other videos on Canvas that were pre-done, there are more examples on there as well. But if I'm given this name, this butane, okay, the molecular formula is C4H10. The molecular formula shows me the total numbers of all of the atoms of each element in the compound, just all grouped together. So C4H10 tells me there's 4 carbon atoms and 10 hydrogen atoms. Doesn't really tell me like how they're bonded or what the molecule looks like or anything. So, it gives me the basic information, but it doesn't give me a lot of detailed information. The empirical formula is where I have it, the subscripts for my formula, they are reduced down to the lowest whole number ratio possible. So for example, if I look back at the molecular formula, what I want to do to figure out the empirical formula is I want to look at the subscripts. And in this case, I had a 4 and a 10. And in my head, I should know like, oh, okay, 4 and 10 are both even numbers. So I know I can divide them by 2. So if I divide 4 by 2, then I get this 2. If I divide 10 by 2, I get 5. And that's the smallest I can reduce it because 5 is a prime number. And so it won't go any lower than that. So if you're ever trying to figure out an empirical formula, simply just look at this molecular formula and then look for a greatest common factor for the subscripts, and then you can divide. Now they all have to divide. If you have one that won't divide, you cannot reduce it, okay? So then we get into, okay, well, how do we kind of draw the formulas to give us more information? Well, we can do what's called the full structural formula, where we show all the individual bonds for in the molecule. And so this usually takes up a lot of space to draw because we're drawing all the carbons, all the hydrogens, and then if there's any other elements, we'll draw them in too. And we're showing all the single, double, and triple bonds and how everything is connected and bonded. So it takes up a lot of space, takes a lot of time to draw that. So a lot of times, instead of the full structural formula, you will see this condensed structural formula used. And this is still going to show us sort of how the bonding is happening, but we're not going to show all the individual bonds to all of these like hydrogen and carbon atoms. Okay. So what happens is this is the same thing as this. They're just written two different ways. So if I sort of highlight, the first carbon here is attached to 3 hydrogens. So that's this CH3 right here. The next carbon, it's attached to 2 hydrogens. And then look, right after it, there is another carbon attached to 2 hydrogens. So those are the same, right? It's both a carbon bonded to 2 hydrogens. So we group them together in parentheses, CH2, and notice it's in parentheses with another 2 outside of it, because there are 2 of those CH2 sections that they repeat, right? One right after the other, okay? And then over here on the other end, this carbon is bonded to 3 hydrogens, so it ends with CH3. Okay, so that's how you would kind of read that if you need to, or if you need to know how to go from the full structural to the condensed, or the condensed to the full structural formula. Okay. Now, the last one on the end here is called the skeletal formula. This is actually my favorite one because it requires the least work to draw. Okay, you don't draw any element symbols unless you have like oxygens or nitrogens or sulfurs. If you have other elements other than carbon and hydrogen, you do have to write those element symbols. But if your organic compound just has carbon and hydrogen, you don't label any of the symbols, because this, by drawing in the skeletal structure, it's understood that at every point, at every corner or vertex, it's understood there's a carbon atom at every vertex or every corner, okay? And it's understood that even though we're not drawing the hydrogens, every carbon is going to have enough hydrogens to fill its octet, okay? So for example, if I look at this one, for butane, right here, right here, right here, and right here, those are the 4 carbons. The corners or the ends are the vertexes or vertices, okay? So because I have 4 sort of points, that tells me there's 4 carbons. And then even though, again, the hydrogens aren't labeled in there, I should know by the definition of a skeletal formula that this carbon here on the end, there's going to be 3 hydrogens bonded to it, because it has to have 3 more bonds to fill its octet and have 4 total bonds. These 2 carbons here in the center, both of these are going to have 2 hydrogens. And that's because they're in the middle of the chain. So they're already connected to 2 other things. And carbon can only connect to 4 things. It can only make 4 bonds. And then the other carbon over here on this end, it will have 3 hydrogens because it's on the end and it's only got a single bond to its other carbon. So all of these are representing the same thing. It's just slightly different ways to do it depending on sort of what information we want or what we're asked to do. And so we're going to start practicing more the next couple of weeks about like for how to draw the different ones, how to recognize them, and then how to also do their names as well. So the second and third row, basically the same thing. So this one, if you notice there's a number in the middle here, that's very common. What that's telling me is that's telling me where the specific like functional group thing is. So if you notice this first one ended in ANE, this one ends in ENE. And as we're about to see later on when we start talking about functional groups, anything that ends in ANE is an alkane, and that means it has all single bonds in its structure. Anything that is an ENE, that is an alkene, and that means that somewhere in the strand of carbon atoms, there is a double bond. And the number tells me which carbon it starts on. So because it's but1-ene, that means that on the very first carbon in the chain, I would find a single bond. And I can see it's right here. So there's the first carbon and it's double bonded to the second carbon. So that's that double bond that gave me that 1-ene, okay? The formulas here, if I look at the molecular versus the empirical, C4H8. And so if I reduce that, 4 and 8, I can divide both of them by by 4. So there's a typo here. This actually should be, let me change colors real quick. This actually should be CH2, okay? Because if I have 4 and 8, they are both divisible by 4, and that would give me a 1 for the carbon and a 2 for the hydrogen, okay? Condensed formula, structural formula, same process. So again, if I look back, and I'm going to erase this highlight that I did here. The first carbon, it's only bonded to 2 hydrogens now. And the reason is that it's double bonded to that carbon. So it only needs 2 hydrogens to complete its octet. So we start off with a CH2. And then the next one, this carbon's only bonded to 1 hydrogen. So notice the next one is just CH. And then the next carbon is bonded to 2 hydrogens. So there's a CH2. And then the one on the other end, it's single bonded. So it's got 3 hydrogens. So it ends with CH3. So again, that's how I kind of go between the full and the condensed structural formula. Now for the skeletal formula, I know that I'm going to have 4 carbons. So it starts out similar to the other one in that we have 4 little vertices or 4 points right here. The only difference now is I have to indicate that there's a double bond. And so what I do is I just draw in this another line here between the first and second carbon to represent this double bond that's right here. Okay. The next one, similar, except it ends in YNE. Anything that ends in YNE, that's got to have a triple bond. So this tells me that the triple bond is going to be between the second and third carbon, which I can see here it is right here in the full structural formula. So going from full to condensed structural formula, my first carbon is got 3 hydrogens, so I got a CH3. My second one, it doesn't have any hydrogens on it. And the reason it doesn't is because it's single bonded to 1 carbon and triple bonded to another. It's already got 4 bonds, so its octet is full. Okay. So here's just the C. And then the next one is also just a C. It's not got, doesn't have any hydrogens either. So let me erase this. I don't like how that works. And then the next one is got 2 hydrogens, it looks like. 2 hydrogens, 2 hydrogens. So notice on this one, they listed the CH2s out. You could do like what on the first example where they were grouped together in parentheses with a 2. So either way you can do it. And then the very last one is got 3 hydrogens. So we end with a CH3, okay? Now this one, if you count the carbons, there are 6 of them, okay? That's why the name starts with hex, because that means there's 6 carbons in the chain. So when I go to draw the skeletal structure, I got to make sure I have 6 points or 6 corners. So I got 1, 2, 3, 4, 5, 6, okay? And then I have to indicate that triple bond between the second and third one. So notice I drew kind of a line on each side of that main chain to indicate the triple bond. So here are some other examples of skeletal formula. This one, and when we get more into doing names next week, because it'll start to make more sense, because it gets to be a little tricky, because you have to find the longest carbon chain. And sometimes the longest chain is this one that goes this way, but sometimes it's not. Sometimes the longest chain is something that goes up and down. So, but on this one, I could count. Okay. On this one, I got 1, 2, 3, 4, 5 carbons. And so I can count the main chain, and then I can see that there are 2 kind of what we call branches coming off of the main chain. And so that's how I kind of figure out how to do the names. And like I said, we're going to get more into that next week. Similar here, I got 1, 2, 3. There's 4 carbons in this one, but I also got an oxygen. So that's going to change the name. Because like where I see these, like here's an OH, here's a double bonded O, here's a double bonded O and a single bonded O. These are all the functional groups that we're about to look at. And so adding those in is going to change the name, and it's also going to change like the properties and things of the compounds. The only other way you might see represented is what we call the stereochemical formula. This shows the three-dimensionality. So when you draw a structure like this, the lines that just look like regular straight lines, like here and here, those are in the plane of the paper. So you got to kind of think of like geometry and think of like a 3D, like an XYZ axis plane type of thing. So those are even with the paper. The dark solid wedge, that would actually be coming out of the paper towards you, like so be coming towards you. And then whatever is drawn with the kind of dashed wedge line, that's going into the paper. So it's going kind of away from you. All right. All right, functional groups, okay? Functional groups are a group of atoms inside a molecule, and like I said, they're responsible for pretty much all the properties. So they're responsible for how they're gonna react, what kind of chemical reactions they can do, and all that kind of stuff. So we're gonna look through all the different examples today, and then kind of your exercises for today are practicing sort of identifying these functional groups. So this one, if you look, it's a long chain of carbons and hydrogens, but here at the end, there's an OH. Anytime you see something with an OH, and it's kind of down here, anytime you see something with an OH coming off of it, that is called a hydroxyl functional group, and the class or the family it's in is an alcohol. So this one up here, if you notice, there's a long chains of carbons and hydrogens. It's got the OH on the end. So I would say the class or the family that it belongs in would be the alcohols. And that functional group, that OH, is called a hydroxyl group, okay? Now, as you go down, there's going to be several different examples. So the three basic ones are the alkanes, the alkenes, and the alkynes, okay? They don't have any other elements. They only have carbons and hydrogens. The difference is the alkanes, their functional group is called the alkyl group because they're all single bonds. There's no double or triple bonds anywhere in here, okay? The alkenes and alkynes have a multiple bond. So if something ends in E, that means that it's going to have a double bond between two carbons somewhere in the formula. And that functional group is called an alkenyl. It's got that En added in there. So you can see the ending of it ends in E, just like this one up here ended in Ane because it's an alkane. All right. The last one on here is alkyne, ends in Yne. So you can see this is the name of this one. And alkyne means that you're going to have an alkynyl functional group, and that means that you will have a triple bond between two carbons somewhere in your molecule. Now, after that, we start adding other elements in. So alcohol, we kind of already saw because that was the example at the beginning. One thing I want to point out, if you see this capital letter R, R is just sort of like the placeholder for like your main chain of carbons. Okay, so anytime you see R, they're just saying there's like a bunch of carbons. It could be 2, 3, 4, 5, however many chain of carbons. And then on the end of it, somewhere you have an OH group that's bonded to it. Okay, so an example here, this is methanol. And so you can see in its formula, it's got CH3 and then it's got OH written. So that would tell me that this would be classified as an alcohol because it has a hydroxyl functional group. Now, as we go down, some of them are going to look similar, so you have to be really careful because the next one, it also has an OH, but it has something else in addition. It has this double bonded oxygen. So if you have both of those coming off of the same carbon, that's kind of the key thing. They have to be coming off the same carbon. This is a different functional group than the alcohol. This is called a carboxyl group. And so the family or the class is a carboxylic acid. And so when you have their condensed formulas, they always have this on the end, COOH, because the first O is the double bonded O, and then the OH is this OH that's coming off of the end of the formula. The next two look really similar, and people always mix them up because both of them have a double bonded oxygen. The difference is where it's placed. Okay, in this one, this double bonded oxygen, it's on the end of the chain of carbon. I know it's at the end because there's another hydrogen coming off of it, and here is the main chain. Remember, the R is like the main chain of the carbons. So in this one, that double bonded oxygen is connected to the carbon that's at the end of the molecule. If it's at the end of a molecule, that functional group is known as an aldehyde. And the family name is actually the same for this one. So the classification and the functional group are called the same. And when you do the name, it ends in AL. And so for them, when you look at like their condensed formulas, it's going to end in CHO, and the O is double bonded. Okay. Now, the next one's called a ketone. It looks really similar because you're like, well, wait a minute, it still has a double bonded oxygen. The difference is where it's placed. If you notice in this one, it's got an R on each side. So it's in the middle of a chain of carbons. It's not on the end like the aldehyde. And so if it's in the middle of a chain of carbons, we call it a ketone functional group, and it's the ketone family. So what it would look like is something like this, where you would have an oxygen in the middle of carbons on the chain. Now, if we keep going, there's a bunch more. This next one is called an ester. So an ester has a double bonded oxygen and a single bonded oxygen on the same carbon in the middle of the chain. So my condensed formula is going to look COOC like that. And on these, they end in a NO8. This next one's called an ether. And an ether just has a single bonded oxygen in the middle of the chain. And so it's got COC like this. So if you see something like this where it's like an oxygen single bonded, that's the ether bunny, because it's an ether and it's got bunnies on it. All right. The next one is the first one that's going to have a different element now other than oxygen, and that is the nitrile. So the nitrile has a triple bonded nitrogen connected to the end of a carbon on the chain. So it'll end like this, CN. Okay. Halogenoalkanes. They have it, the functional group is called a halogeno something. And so halogeno is kind of generic because it could be any halogen. So in this one, it's specifically chloro because it's chlorine. So that would be a chloroalkane if you wanted to be specific, but you can just say halogenoalkane, that's fine. All right, so the last few on here, there's this one called, the classification or the family is called an arene. The functional group is called the phenyl group. So phenyl means that you have one of these hexagons with a circle in it, okay? I want to say it also might look slightly different when it's drawn. It might not have the hexagon with the circle, because that hexagon with the circle we learned in topic 4 means that there's resonance. So it means that there's some double bonds in here that could be in multiple locations. So you might see it drawn like this, where the double bonds are alternating every other bond, because these are the two resonance structures. And so really we draw this hybrid structure and we represent it like this with the hexagon with that circle in the center to show that those 3 double bonds are really like they're resonating and they're moving in between all of them. Okay. So anytime you see that, that's a phenyl group. And then that would be the classification for an arene. Okay. The next one is an amine. So this is why things start getting complicated, because the names sound similar. Some of them are only different by like a couple of letters, and some of the structures look similar as well. But the last 2 sections on here, amine and amide, so they're different by 1 letter, but when you look at their structure, an amine is going to have an NH2 group on the end of a chain. So here's what this condensed formula would look like. And amide, it will have the nitrogen possibly with 2 hydrogens, but it will also have a double bonded oxygen. So it looks like this, O and then NH2. So if it's got just the NH2, it's an amine. If it's got like the NH2 and a double bonded oxygen coming off the same carbon, that would be an amide. And so the functional group on that last one is called a carboxamide. So all this to say that for today, your main practice is going to be looking at these, and you don't need to tell me like how to name it or anything. I just want you to tell me what's the class and the functional group. Okay. So what you'll have to do is kind of look at them and kind of look for what's different. Okay. Because that's usually how you're going to tell is what's different about it. And then that helps you to figure out how to classify it, which functional group it has. So most of them are going to have 2 answers. There are a few up here, like the amine doesn't have a different name for the functional group. The nitrile, the ether, and the ester don't really either. And then ketone and aldehyde, their names are the same. But the rest of them should all have a class and a functional group. Okay. So there's several on here. Some of them you may use more than once because there are going to be some on here that duplicate.